Welcome back, folks. Here's our last passive component for this class. There is one more passive component. It's called the memristor, but we're not going to cover it in this class. It's not commercially available yet. It's still in labs. It's kind of theoretical still. The inductor is a little different. I find there's a lot of misconceptions around inductors. So I'm not quite going to go to the physical components. I usually stop the class and say, okay, what's an inductor? And I'm looking for the wrong answer. So how would you answer that? What's an inductor? And most people come back with saying it's a coil of wire. And I go, well, you're not wrong, but you're also not 100% right. Everything that we flow current through, I should have grabbed a prop. Luckily, my office is a mess, and all I need to do is look on the floor, and there's scraps of wire. Everything that we flow current through has some inductance. It's usually so small that we ignore it. Okay, I can say the same thing about resistance. I have this little chunk of wire, and it has some resistance. It's just very, very low compared to everything else around it. This little chunk of wire also has some inductance. It takes a little bit of time for the magnetic field to set up around it when there's a change in current. Okay, in order to get a lot of inductance in a small area, we usually coil it, and that causes the magnetic field to fight itself. And that's where a lot of people think, oh, an inductor is a coil of wire. Well, that's not true. A coil of wire has a much larger inductance and a smaller form factor than if we had just a long stretch of wire. This one's really tiny. We can ignore it most of the time. If you're talking about a transmission line, if you're talking about sending power over a long distance, go outside, look up at the power lines. I don't know when you're watching this, but I'm recording this right after that huge tropical storm that came and hit us over the summer. So your power lines are hopefully back up by now, but I hear some people's aren't yet. Mine are. It's so long that you can't ignore the inductance anymore. So this misconception kind of, for a long time, that's how I was taught. It's a coil of wire. And if I go look at a textbook, it makes me think that it's a coil of wire. But then when I started talking about longer transmission lines or high-speed stuff, if we talk about circuit boards, which you'll do in a future class, then we can't ignore that really small inductance because it's switching so quickly. Same could be true about the leads on a component. I'm trying to teach you better than I was taught. Okay, apologies to my professors; they were good, but I want to kind of hammer that home as much as I can. Okay, so I'm not going to quite go down to physical properties. Go take an EMAG class if you want to dig into that. It's a rich and wonderful topic, but it would take a whole semester, just about. Okay, so our schematic symbol for the inductor totally doesn't help. Okay, beat this misconception because it looks like this. Okay, it's supposed to be like a little coil of wire, rounded instead of jagged. So the resistor, my horrible resistor, looks like that, and the inductor would look like that. Okay, if you want the Euro style inductor, it actually looks like this. So you may see that if you're practicing in Europe. Okay, but we're not. We're in New Britain or wherever you are. And that's our schematic symbol for the inductor. All right, the variable for inductance is capital L. I think it's French for l'inductance. I don't know. I can't remember that one for some reason. And the unit is the Henry, okay, named after yet another dead guy. So it's capital H, okay. Okay, so there's our inductor symbol. We have the variable, we have the unit. We play the same game where we can have equivalent components. So if they're combined in series, life is good. Inductors play nice. They play the same as resistors. Okay, so when they're in series, let me just draw this out here. Okay, L1 and L2 for those inductances, and this is A and B. Then the inductances add. Okay, so LAB is equal to L1 plus L2. Okay, when they are in parallel, well, their inverses add. So what's the inverse? So inverse of inductance, come on, inductance is what we call reluctance. Okay, ooh, reluctance. Reluctance. Okay, now let's just get that up a little higher. When the two inductors are in parallel, the reluctances are going to add. So the variable for reluctance, I guess I should get it over here under the word reluctance. Apparently we were running out of variables, and rather than just using a nice Greek one, they said, well, R is already resistance, so what do we use for reluctance? And somehow we ended up with a script R. Forgive me, I don't draw many script R's, only when I'm talking about reluctance. Okay, so it's a script R, and the unit, and I love making people guess this one in class, right? For farads, the inverse was derads. For henries, the inverse is, well, it's the inverse Henry. Okay, we lost our imagination and we just said, bump that. Let's use the inverse Henry, okay? And it's going to be capital H to the -1 when we write it out. Okay, so that's reluctance. So in parallel, reluctances add. Okay, so if I take two inductors and I'll draw them horizontally this time, doesn't matter as long as they're connected to the same two nodes, right? Have I repeated that one enough? Are you sick of me repeating that? Because I'm going to repeat it a few more times this semester. They got to connect to the same two nodes to be in parallel. Okay, so we play the same game where we have 1 over, I got to write this script R. Totally going to cheat in a second here. Hold on. Script R. Oh, hold on. If I'm going to cheat, I should do it right. Right. There's my script R. AB equals 1 over the first reluctance and 1 over the second reluctance. Okay, and then of course we solve that for RAB, so it just ends up being 1 over the first one plus 1 over the second one. Okay, and then add terms as necessary if you have more. Oh, it's all behind me. Woo. If you have more inductors in parallel, just add them here. Okay, for only 2, we get the same limitation for only 2 inductors. Then we can do the product over sum game. How many of these do we need? We need 4. All right. Get them all in one shot, and then I'll fill in the subscripts. Okay. So we can take the product over the sum. Okay, but that only works for 2, so be careful with that one. Okay. So we can combine inductors when they're in series and in parallel, which is useful some of the time. What's useful all the time is understanding how we relate voltage and current. See if I can spell relationship right the first time, unlike the last video. Okay, so again, you'd have to go back and take a lot more electromagnetics or pay attention in your physics class. What I'm interested in is what we need to use to perform circuit analysis. So for this one, the voltage as a function of time, so this is a time domain function, so go back to your pre-cal, that's the domain of the function is time, is equal to the inductance L times the time derivative of the current. Okay, that's a lowercase I. Okay, so it looks similar to the capacitor equation. This is our what we call the inductor equation. Okay, it looks similar to the capacitor equation, but we have V equals L di dt. For the capacitor, it was I equals C dV dt. Okay, so we're taking the voltage and the current and we're swapping places. But that's one of the things that we're definitely going to need, and that's also going to lead to some differential equations, and we are going to avoid those by using phasors. We're going to get around it by using phasors. Okay. We can, of course, rewrite that in the integral form. I do try to avoid the integral form when I'm analyzing circuits, but sometimes you can't avoid it. You just gotta, can't share that expression on tape. There's an old expression my mother said. Sometimes when you have to do something you don't want to do, you should just go over and do it. Let's just leave it at that. Sounds better in her native language. Okay, so we're taking the time derivative of the voltage, or the time integral of the voltage. We got to be careful with our variables of integration, so we're going to substitute in tau again. And once again, we have this initial condition. Okay, so you might see that form as well. It's equally valid, but a little more difficult to work with when we're writing our KVLs, our KCLs. We're going to be using these forms when it's appropriate. Okay, that's what I think you need to know for inductors. The next step is, how do we use all of this information to analyze circuits? And that's going to get a little more interesting. Okay, so I'm not sure what I'm going to do next. I got to go figure that out. I know what I do in class, but I think it's going to play a little different here. I'm going to take a break, think about it, eat some lunch. You should do the same. Stay tuned and good luck, folks.